so continues our discussion about lossless transmission line based on the assumption that omega L is much bigger than R and omega C is much larger than G, the conductance. The propagation constant can be rewrite, and by acknowledging the fact that R over J omega L and G over J omega C are relatively small, very close to zero, we can use this relationship to simplify the representation. Here we have, well, as you can see here, we have three terms. The first term is imaginary number, so it represents it corresponds to the phase constant beta. The second and the third terms are real number. We apply real number because the J omega term cancel each other, so it represents the attenuation part. So the attenuation constant alpha can be recognized as this one. They cannot be ignored as long as R, G, or C are numbers, actual numbers. So that represents the low C part. Nevertheless, the phase constant beta and the propagation velocity Vp are pretty the same as the lossless transmission line. So continue to the next page. Here we have the expression for the characteristic impedance. Originally, this is a relatively complicated expression because R and GC are all taken into account. However, using the same approximation technique presented in the previous slide, the thing in the denominator, because the second term is relatively small, so it becomes 1 minus G over J omega C. Okay? And the denominator term remains here. So you notice that the equal marks become approximate mark because we have already taken the approximation of small number, the so-called small number approximation using that principle. And the expression can be further simplified by using the small number approximation principle again. So here you have the square root, which is 2 over 1, right? So the small number approximation becomes 1 over 2 times R over J omega L minus G over J omega C. Note that in the previous slide, the two terms cannot be neglected because they are a real number, a positive real number plus another positive real number, so they are a real number. However, in this way, in this case, this is a small number minus another small number. So it becomes even smaller. So based on the knowledge that the two are minus, they are kind of cancel each other out. So this expression can be further simplified as square root of L over C, which means that the characteristic impedance of a low-loss transmission line is about the same as lossless transmission line, which makes our life much easier. Alright, so by identifying that the characteristic impedance is not much different from the one of lossless transmission line. So the low-loss transmission line in the calculation or in the description of a low-loss transmission line, we only need to account for the attenuation part. We only need to account for this non-zero alpha, non-zero attenuation constant. All the other parameters, the phase constant, the velocity of propagation, the characteristic impedance, are about the same as lossless transmission line. Okay, so that's probably the only thing that we need to modify. Okay, so for a low-loss condition, that is, omega L is much greater than R, omega C is much greater than G. And this condition is valid for what? For very high frequencies, which means omega becomes becomes larger and larger, or for very small value of R and G, if your transmission line quality is relatively good, which means the lossy mechanism, the Ohm's laws, and the dielectric conductivity are relatively small, then the low loss condition can be satisfied. So as we already pointed out, for the general case, it's more convenient to determine experimentally for the value of Z sub 0 and the propagation constant gamma, then you need to compute it then analytically. 就是说用做实验来比较快啊，你就知道哪一个传输线做出来，然后稍微量一量，那就可以得到够实用的那个参数来去做传输线的设计 ，OK？ 传输电路的设计。So next, let's modify our transmission line equation a little bit by taking into account of the lossy mechanism. All right. So I guess we have analyzing the two equations. They are the voltage expression at a different position Z and current expression at different position Z, using the positive going component and negative going component V plus and V minus, and we know that the index, the index of the exponential becomes exponential minus gamma Z and exponential gamma Z, which taking into account of the attenuation constant. However, in the following derivation, we would like to introduce a modification by replacing Z with D. As I guess about 2 weeks ago, when we start our description about chapter 7, we already say that we can use minus D to replace Z. Why? 我有点忘记了 Z 跟 D 的差别在哪里 ？OK， Z 是以左边的 generator 为起点，所以 Z 等于0在最左边然后最右边是 Z 的最大值。D 是要从另外一个观点来去描述那个传输线上面的位置吧，所以对 D 来讲的话，它的起点是在最右边所以我们那个距负载低处所以 D 指的是从最右边往左边看所以越往左边的 D 值越大所以看你是从哪边走到哪边所以你可以选择用 Z 来描述或用 D 来描述所以在接下来的这个讨论，我们用的是 D 也就是 D 等于0指的是最右边然后 D 越大的话是往左边走So in the following discussion, we adopt the location representation in terms of per meter D, which is the distance from the load to the right. So D equals to 0 at the very right end, and D becomes larger and larger as it goes to the left. So first, let's substitute the transmission line equation, the voltage and current representation on the transmission line. As you can see, we still have two components. One goes to the right and the other goes to the left, but you replace Z with minus D. Okay, so they appear in this way. And here we collect the second and first term by taking out the exponential gamma D term, the common exponential gamma D term. So you have 1 plus gamma D and 1 minus gamma D. So gamma is what? Gamma is the reflection coefficient. Alright? And the reflection coefficient can be expressed anywhere on any place on the transmission line. Alright? So D is the reflection coefficient. What is the reflection coefficient? What is the original definition of the reflection coefficient? Gamma D will be defined as V minus D over V plus D. The negative going and positive going components on the transmission line are like this one, right? Okay, so if you replace with B, so what is this term? What is the significance of this term? V minus is the B minus components at the load. 好了，也就是那个 d 等于0的时候，在 load 的那个位置，这个是 V 正是在 load 的那个位置的 V 正，OK， 所以它的后面会跟上这个 exponential minus gamma d 跟 exponential gamma d， 加上对那个传播距离的描述。但你要注意到的是 exponential gamma d 跟 exponential minus gamma d， 因为 gamma 已经是一个 complex number 了，所以这个描述里头包含的不仅仅是相位的变动也就是你距离那个传输线的负载那个位置一段距离 d 之后，你的讯号不仅相位有所改变，大小也会有所改变，大小也会有所改变。也就是说，假如我们用画图来看，本来是 V 正 D 的讯号从这边往这边走，所以这边走的时候，它变成 V 正。其实 V 正跟 V 正 D 其实就是 D 等于0啦，跟 V 正 D 它们有什么不一样？相位不一样嘛，对不对？因为跑了，所以相位不一样。还有呢，大小也不一样。因为你是在 lossy 的 transmission line 嘛，所以谁大谁小。这边往这边跑所以这边比较大，这边比较小。然后这个跑到负载之后呢，有反射系数嘛，伽马，然后它就弹回来，变成是 V 负。那这边看到的是 V 负 D。所以 V 负跟 V 负 D 有什么关系？相位不一样嘛，对不对？大小嘞也不一样，谁大谁小？这个大，这个小，对不对？这个大，这个小，为什么？越走越小嘛，所以这一边的伽马 D， 也就是 V 负 D over V 正 D， 跟这边的伽马，也就是 V 负跟 V 正。他们两个会不会一样大？注意我们在前面2个礼拜里头在讲 Chapter 7的时候，都跟你讲做 Constant SWR Circle。为什么？为什么说 Constant SWR Circle？ 因为我们之前讲的传输线都是 lossless 的传输线，所以一旦负载决定之后，它在传输线上面任何一个位置的反射系数的大小都是一样的。可是在这里头，伽马 D 跟伽马它们的大小会有什么关系？这个一定小于这个，耗损嘛，对不对？这个东西会比这个大，这个会比这个小，所以这一个的绝对值会小于这个绝对值，好不好？把这个记起来因为等一下我们要讲那个 example 7.8 那个例题。要去考虑说传输线里头的能量传输到负载的功率跟这些事情都有关系，好不好？后来 so what 这边伽马这边课本这边标伽马 R 了 ，OK， alright。So in this slide, we try to discuss the relationship between the reflection coefficient gamma at specified position location D and the reflection coefficient at the load, which is gamma R. So gamma D, by definition, is V minus of D at D over V plus at D, which can be replaced with V minus, as I already draw on the board. V minus is the voltage, negative going voltage at the termination, times exponential minus gamma D. This adjusts the magnitude and the phase due to the return propagation, the propagation to the left. And for the V plus part, it can be represented as V part times exponential gamma d. So the exponential gamma d stands for the phase and magnitude change due to the propagation from left to the right all the way to the termination. So by identifying this 2 as gamma r, the reflection coefficient of the diode, and identify this part as exponential minus 2 times gamma d. You have this. And because gamma is a complex number, so this term can be separated into a pure real number, pure imaginary number. So you have exponential minus 2 times alpha d. This is a real number. Now, and it stands for the propagation loss. Now, and the 2 suggests you taking the round-trip propagation into account. 因为你讯号是去了再回来嘛，走2次，所以你就有一个倍数2。那后面那个呢 ，minus J2 times beta d stands for the round-trip propagation phase change, which is similar to what we have for lossless transmission line. Okay, so this is an important relationship that you need to identify about the reflection coefficient at a different place on a lossy transmission line. Okay, again, for lossless transmission line, the reflection coefficient magnitude is the same everywhere. Only the phases are different. Only the phases are different. However, for a lossy transmission line, not only the angle, the phases are different, the magnitude are not the same. The longer the transmission line, the smaller the reflection coefficient. Well, tell you a story about 20 years ago, the antenna design is kind of, small antenna design is kind of a beginning phase. So due to the emergence of personal wireless communication gadgets, say the cellular phone, we have a bunch of the so-called small antenna design. So if this is the phone, and you have a small antenna over here so that you can access the base station for 那时候还在讲这种 2G 最多到 3G 2G second generation signal or third generation signal. And one criteria for the evaluation of antenna is the so-called reflection coefficient, or S11, which is not the same as the reflection coefficient. And for an antenna, if you look at the reflection coefficient spectrum, the horizontal is the vertical is the gamma or S11, and the horizontal axis is frequency. So at an operating frequency, you want the S11 level to be small, which suggests most of the input signal are radiate out from the antenna. However, if for some poor design, you have S11 like this, which means only about 50% of the energy that goes into the antenna gets radiated, and another half get reflected back. So it's a lousy design. How to fix that? Well, I've seen this many times. They draw a transmission line all the way from the antenna to the bottom to provide a connector, say SMA connector. And with this modification, the S11 looks much greater, looks much better, like this. Why? Because the transmission line is lossy, it's absorb most of the reflected signal. So the reflection coefficient gamma becomes favorable, meet the specification. So, well, of course that's cheating, right? So once you know the principle about transmission line, you know that the good reflection coefficient level is obtained in terms of the loss on the transmission line. It's not the antenna itself may be pretty lousy, right? Okay. 好，过来。Okay, so in the previous slide we already derived the representation of reflection coefficient gamma at a specific location D in terms of the reflection coefficient at the determination and the magnitude and phase adjustment due to the propagation on the transmission line distance D. And we can also write out the input impedance Z 输入阻抗对于传输线的设计、传输线的匹配，我们要看的其实最直接要看的是输入阻抗，而这个输入阻抗 input impedance can be derived from the reflection coefficient. So it's not a big deal once you have gamma. Once you have the expression for the reflection coefficient, you can substitute the definition of ZD, which is the ratio of VD over ID. It equals to the characteristic impedance Z sub 0 times 1 plus gamma over 1 minus gamma. So you substitute gamma D with this number like this, so you end up with this relationship. Note that here we use L, so it stands for the distance of your observation position. All right. So L, so you replace D with L like this. Okay. And with some massage about the equation. 人喜欢用这个把细的整理一下，再把它马杀鸡一下了所以你会看到这边它把伽马的表示是带回它原来的表示是 ZR 减去 Z0 over ZR 加 Z0 所以从这一步到这一步，它主要动的是那个伽马 R 用 ZR 跟 Z0 表示。所以这边下来之后，它把它整理一下，把下面分母的那个 ZR 加 Z0 乘上去，所以变成这样子。然后你会看到了，它其实是两个指数的相加减也就是说这个是 exponential minus 2 times gamma L， 所以你上下都乘上一个 exponential gamma L， 那它就会形成是这个形式exponential x minus exponential minus x 所以从这一步到这一步，它做了两件事情，一个是分子分母都乘上 exponential gamma L。然后第二件事情呢，把 ZR 的ZR 是相加的，所以它变成 ZR 这个叫什么 hyper cosine of gamma L。The second term is Z sub 0 term, which is Z sub 0 times exponential gamma L minus Z sub 0 times exponential minus gamma L. Because of the minus sign, it becomes hyper sine. So you have Z sub 0 hyper sine of gamma L. And you do the similar thing for the denominator part. So you still ZR and Z sub 0 on the R. However, the order of hypersine and hypercosine are swapped. So here you have hypersine and hypercosine. And 1s is divided the denominator and numerator with hypersine. Okay? So once you divided the top and bottom of the equation with hypersine, you end up with hypertangent. Okay? Like this. So it's ZR plus Z sub 0 hypertangent of gamma L divided by ZR hypertangent of gamma L plus Z sub 0. Well, of course you don't need to memorize this equation, alright? You only need to know that the input parameters can be calculated or computed analytically. So it's not a very difficult result. But you need to know this relationship. Okay? So take a few looks at the equation and memorize it. 稍微有个印象了，好不好？稍微有个印象，也就是说，你有了 Z0、ZR， 有 gamma L 有了对于传输线耗损的了解，有了对于负载的阻抗的了解。事实上，你经过一段传输线之后，你的输入阻抗是可以被正确的描述出来的。只要你知道你的负载是什么样子，那你在传输线上走了多久，传输线的耗损常数阿法，传输线的相位常数贝塔是多少？只要知道的话，其实都可以写出来，好不好？好。Alright, and the last thing that we need to describe is the power flow. Let's look into the signal on the transmission line in terms of power, from the perspective of power. So here is the what is this? P with two. Well, I don't know how to describe that. This is what? What is the significance of this sign? Time average. Okay, so that's the time average power delivered to the transmission line system at position D. So that's the average power passed through position D. That can be expressed as half times the real power of voltage at position D times the complex conjugate of current at position T. This equation is valid only for what? Only for sinusoidal signal. So this expression is only valid for sinusoidal signal. That is sinusoidal signal of a certain frequency, and this is the time average power. Time average power. Alright, so what to do next? What to do next is to substitute your known representation about voltage at D and the current at D. Know that here is the voltage at D expressed in terms of the voltage, V plus voltage at the termination. 负载的那个电压，这个是负载电压，这个是传输的调整，然后这个是反射系数的调整，反射系数的调整。注意这个反射系数是在左边的反射系数，左边的反射，D这个位置的反射系数，然后后面是那个电流的 complex conjugate 的表现，所以它是 Z0 的 complex conjugate、V 正的 complex conjugate， 还有这些东西的都取 complex conjugate。不过幸运的是，因为我们讨论的是低耗损传输线，所以 Z0 还是一个实数，所以你那个 Z0 的 complex conjugate 这边还没有把它拿掉，不过后面会把它拿掉，等一下我们再讲。好啦，先留着吧。Z0 的 complex conjugate 那个 star sign 代表是 complex conjugate 嘛，先留着。然后呢，你要注意的是 exponential gamma D 跟 exponential gamma complex D 是啥意思？也就是你的 gamma 值的 complex conjugate 也要取所以本来是 exponential alpha D exponential J 贝塔 D， 这个是 exponential， 不要这样写，这个是 exponential gamma D 嘛，那exponential gamma conjugate D 的就应该等于什么？就应该等于 exponential alpha D exponential 负的 J 贝塔 D。取 complex conjugate 之后它变负的，所以这两个相乘的结果就变成什么 exponential 2倍的 alpha D， 那就会把抵消掉了，所以就相乘的结果会直接变成这个东东， 所以你看到的这两个相乘就跑到这里来。然后你要 identify 的是这两项跟这两项的相乘，它就会变4项。这一项是1乘1，这一项呢是伽马 d 乘上伽马 d 的 complex conjugate， 所以是它的平方。然后这是伽马 d 减去伽马 d 的 complex conjugate。然后下一步要 identify 什么？下一步要看一下他们谁是实数，谁是虚数。谁是实数，谁是虚数？这一块是实数，这一块呢，也就是这边相减的结果，这边相减的结果是虚部。那你因为去取实数嘛，前面有一个取实数的动作，所以这一项就没了吗？Not so fast， not so fast。理论上你要看一下这个 Y0 正，Y0 complex conjugate。Y0 本来应该是什么？Y0 本来应该是 G0 加 JB0， 对不对？然后那个这边其实但是它是 complex conjugate 嘛，所以它变成是减的 JB0。但是我们这边要偷偷告诉你一个小技巧因为我们假设的是 low loss transmission line， 所以那个 B 几乎等于0 ，low loss 嘛 ，low loss 所以它的 Z 值、它的 Y 值几乎都还是实数，所以它 B 值等于0所以既然 B 值等于0，那这项就不用写了，所以我们只要考虑前半部就好了因为 B0 几乎等于0。所以我们看下一页。So let's take a look at the next page. Well, that's still a more complicated representation. However, 我看一下，我不跟你讲什么。好，这边没有讲出来，但我们在例题的时候会跟你讲这件事情也就是说，理论上这边看起来有点复杂后面还跟着这一项，但其实这一项最后不用算为什么？因为 low loss line 嘛，所以那个 B0 假如是几乎等于0的话，这一项就没有了，我们只要考虑前面这几项就好了好，所以这个是它的表示式这边回去真的一定要看不然你不会去算那个 example 7.8你也不会去，你就没有办法算那个期末考的那一题好不好？我每年都会考这一题，考古题也有，好不好？所以第一个 example 7.8要会算，考古题的这一题要会算。好不好？这样你大概就有60-70%的把握去应付期末考的这一题，好不好？传输线的 power 的耗损，好不好？这是你在讲传输线的 power flow 最基本的题目 ，OK？ So let's take a look at example 7.8. It takes into account it has 3 questions. What is the time average power delivered to the transmission line system? That is the power goes to the right of this interface from the generator into the transmission line. The second question is the power delivered to the load. The time average power goes into the termination. The third problem is the power attenuates on the transmission line. Right? So that's quite straightforward. If you get the first one and the second one right, the difference will be the loss occurs on the transmission line, right? So the power, the energy goes into the transmission line minus the energy dissipated on the transmission line equals to the energy that goes to the termination. So here are some description about the problem. In this case, the load is 150 ohm, which is purely real. The characteristic impedance is 15 ohm, so we know that it's a real number, so it suggests that this line is low loss. However, the alpha value is non-zero. Note that the alpha value is labeled as 0.01 10 to the minus 2 meter per wavelength. So be careful about the unit. It's described in terms of wavelengths. And what is the length of the transmission line? 10.2 lambda. Alright? So 10.2 lambda. So 看一下 alpha 等于 0.01 per wavelength 什么意思？意思是什么？它走一个 lambda 之后，它的功率会耗损掉多少？1%，对不对？因为进去的是1嘛，出来是0.99，0.01是耗损掉的，所以过去的是多少？0.99，那是一个 lambda。那请问10个 lambda 呢？出去的是多少？出去的是多少？0.99乘0.99乘0.99乘0.99乘0.99乘0.99乘10次，所以至少是，因为每一段都要耗损1%啦，然后它有一点复利效果嘛，对不对？所以走10个 lambda 至少耗损掉 10%， 其实会比 10% 再多一些啦，但你大概可以估一下啦，因为一个 lambda 是1%，所以10个 lambda。至少是 10%， 事实上比 10% 要多一点。我们刚才讲了复利嘛，但它是一个 low loss transmission line， 不然的话，它的Z0不会是纯实数。OK， alpha 不等于0的话，其实Z0会是 complex number， 但是在这里它还是用50，所以要告诉你的是，有耗损，但耗损不算很大了，所以它的 characteristic impedance 还是差不多是一个纯实数，用50就好了。OK。Alright, so the first thing is calculate the reflection coefficient at the determination, that is ZR minus Z sub 0 over ZR plus Z sub 0, which equals to 0.5. Okay? And the reflection coefficient gamma R can be translated to the left, to here. By which distance? By 10.2 lambda. So we need to calculate the reflection coefficient at the left end. That is gamma R times exponential minus 2, wrong trip, 2 times gamma L. And 2 times gamma L can be separated as exponential minus 2 alpha L and exponential minus J2 beta L. And of course, you need to substitute L, which is 10.2 lambda. And alpha equals to 0.01. So the first term is minus 0.204. Okay? So you need to use your calculator to tell me what is this number. This number is about 0.8. A little bit greater than 0.8. 所以 0.99 乘10次之后大概是 0.8 多了。所以你会看它从 0.5 变成 0.4077。其实那个4071就因为这个东西大概是0.8左右所以自己乘一下，验证一下。那第二件事情是相位的改变。So the second term involves with the phase change only, and the reason why it says that it's the length is 10.2 wavelengths, which actually suggests you that you need to only calculate 0.2 wavelengths, because the 10 wavelengths part is corresponding to 10 times 20 times 360 degree. So you don't have to calculate that. In fact, it's minus J 30.8 pi, and every 2 pi it goes back to the original place. So you need to account for 0.8 pi. Okay, so which is about minus 144 degree. Okay? Be sure you understand how to come up with these numbers, right? 拜托我跟你讲的嘛，期末考一定会考这一题的，期末考一定会考这一题的，20分到25分，就在这里了。你真的7点8去练习一下，考5题心理练习一下，好不好？ So we have already derived the expression for the reflection coefficient. Here in this slide, we try to derive the expression for the input impedance. Z, which is the input impedance at L equals to L, okay, to the left hand, all right? And by definition, ZL equals to Z sub 0 times 1 plus gamma over 1 minus gamma. So substitute the gamma values that are calculated in the previous slide, which is 0.4, and the angle is minus 144 degrees, like this. So be sure you are, make sure that your calculator is your best friend, so that you can use it to find out the number, okay? From product format to real and imaginary part, combine the two numbers on the denominator and numerator and change it back to the polar form, and do the division by dividing the magnitude and subtracting the angle. You end up the polar form of the input impedance. And you can change it back to, not necessarily to change it back to the real imaginary part. 我都接受了，这答案最后答案是这个或这个都 OK 了哦。这是 polar form 这个是 complex number form。所以这是你的 input impedance 所以 input impedance 是一个26 ohm 表示什么？电压是电流的26倍。但注意后面跟着一个负30度的表示什么？电压落后电流30度所以 input impedance 不一定是实数它假如是 complex number 的话，表示电压跟电流不同相位。好了，接下来了我说你要练那个练习题，你就要去适应那个题目做题的节奏，好不好？下一个问题问什么？刚刚算出来的是输入阻抗 input impedance。下面一个问题就是从 input impedance 去算有多少的 current, calculate how much current is delivered to the transmission line. With the current amount found, you can calculate the voltage at the input end. All right. So here is the derivation of the currents calculation, which can be found using the voltage division equation. Vg, the generator voltage, divided by generator inner resistance of the generator and the input impedance of the transmission line. So substitute those number, you come up with the current, which is 1.3 amp, with a phase of 45 degrees. And use the currents and the input impedance. The current and the input impedance, you can compute the input voltage. That is taking the product of the two, and you have the voltage magnitude is 35 volts, and the phase is 15 degree for your voltage at the input end. Now you have the voltage, you have the currents, you can calculate what? Power, time average power. That is half of the real power of the product of the voltage and the currents complex conjugate. Okay, so with all the number in the previous slide, you calculate this number like this. Okay, so you end up with the power, time average power delivered to the transmission line system, which is 20.3 watt. All right. Next, we would like to know the power delivered to the load. Here is the power at the left end of the transmission line. Next, you want to find out the power delivered to the right end of the transmission line at the load. Here it says B sub 0 equals to 0. Why? Because at the very beginning of the problem description, we will tell you that the characteristic impedance Z sub 0 equals to 50, which means it's low loss. The imaginary part of the characteristic impedance and characteristic admittance is nearly 0, so B sub 0 is 0, which means this equation can be greatly simplified by neglecting the very last term. You only need to worry about this one, gamma D, and G sub 0, that is essentially the real power of the admittance, which is because the characteristic line is characteristic impedance is 50, so G sub 0 is 0.02 50的导数嘛 0.02。那2倍的 alpha D， 我们 alpha 值刚刚也有出来了嘛，好吧？事实上只是把这些值套进去 ，OK？So V plus 这一题的一个重点是要你要搞清楚这里头的那些代号、那些参数，指的是什么？这个参数指的是什么？这个参数指的是在最右侧的 V 正电压，好不好？So this one stands for the voltage delivered to the load, to the termination. So using this equation, you can have this expression. Modify the equation a little bit. So here's the time reach power delivered to the transmission line circuit, which is 20.3 watts. And here is the attenuation of this round-trip attenuation. And here is the reflection coefficient at the left end, and here is 0.02, as you can see here. So they are all the known numbers. And here you have the voltage at the termination is 44.58 volt. Okay. So here's the voltage, and what is the power? Well, next. You can use the same expression. You can use the same expression for the time reach power. It equals to 0.5 times voltage V plus to the square times G sub 0 times 1 minus reflection coefficient magnitude, which has already been calculated. So substitute the value you have 15.9 watts. Okay, so that's the power delivered to the termination. And the very last question is how much power is lost on the transmission line, which is the difference from the power delivered to the transmission line and the power delivered to the load. Okay, so it's about 5 watt 考试的时候记得检查一下你算出来的数字合不合理也就是说你那个 alpha 要是这个 alpha 是算是相对小的所以你会看到进来20瓦，进去15，出去14瓦、15瓦所以中间耗掉5瓦假如说那个 alpha 值大的话，那可能进来20瓦，最后 deliver 到 load 可能不到2-3瓦之类的那它耗损就很多了，17、18瓦但注意耗损不会是负值啦，对不对？它 deliver 到那个 load 的那个数字也不会是负值所以算出来负值的条形自己从物理上面去检查一下，好不好？好，那我们这学期的课程都在这边好吧？下一个礼拜好好的准备一下了希望大家都能够阿弥陀佛吧